Earlier in this unit, we talked about something called the motor effect. We didn't use that term very often. A couple times we mentioned it, but for the most part, we just described it rather than using a name for it. The motor effect occurs when you have a charged particle moving through an external magnetic field, or a wire that carries a current in an external magnetic field. What happens in that case? You get a charged particle moving through a wire, moving through the air, that's exposed to an external magnetic field that's pointing into the page. That wire experiences a force. So in other words, a current in a magnetic field causes movement. Got it? That's a motor. That's an electric motor, right? When you apply a current in an electric motor, there's a magnetic force on the wire starts spinning, and that's how the wheels on the electric car turn, or that's how the bit on your drill turns. That's the motor effect. Now the generator effect is the opposite of that. Instead of saying you've got a current in a magnetic field which causes a force on the wire, this time we've got a force on the wire in a magnetic field that causes a current. So in other words, instead of our current causing movement, we've got a movement causing an electric current. This is how we generate electricity in almost every case in terms of at least electricity going on the power grid. Okay, the exception to that would be solar energy. If solar energy is put onto the power grid, it's not generated this way at all. Okay, but if you've got wind power, it's the way it's generated. Okay, you got a force, it's a wind force on wire basically, which moves the wire, and that causes an electric current. Same thing happens with coal-fired power plants, which is how we generate most of our electricity in Alberta, is by coal-fired power plants. Coal burns, generates heat, boils water, causes steam when the water boils. That steam rises, moves a wire, essentially moves a wire, and generates an electric current. So we learned about current in a wire in a magnetic field causing a force. Now we've got a force, an outside force on the wire in a field which causes a current. We're generating electricity by movement rather than generating movement by electricity. So the generator effect is the production of electricity by magnetism. It was discovered by two separate guys, independent of one another, two separate continents even. 1831, 12 years after Ørsted's discovery. Remember Ørsted's discovery, 1819, 200 years ago this year? Electricity generates magnetism? Well, here we go. Magnetism generates electricity. Took a while to figure out the first one, but once we figured out the first one, it only took 12 years to get the second one. Electricity makes magnetism, magnetism makes electricity. Michael Faraday, an English guy, and Joseph Henry, an American. For whatever reason, it's usually Faraday whose name we see associated with this. So if you're going to remember one of these names, remember Faraday's name. Now, when we learned about Ørsted's discovery, there were no caveats to it. If you had electricity, it always generated magnetism. Zero exceptions. You have a simple electron moving through the air, it generates a magnetic field. If you have the electrons moving through a wire, it generates a magnetic field. If you have electrons going through the wires in your wall, it generates a magnetic field. I mean, to the extreme, if you have a balloon that you rub against your hair and you throw that balloon across the room, it generates a magnetic field. It would be a very, very weak magnetic field, but still a magnetic field nonetheless. There was no caveats to it at all. If you had moving charges, you generated magnetic fields. Now, magnetic fields will generate moving charges as well, but there are caveats to this. It doesn't always work. In order to generate a current from a magnetic field, you need to have a conductor or a wire and a magnetic field. All right, stands to reason, right? If you want to generate a current in a wire from a magnetic field, you need a wire and a magnetic field. And one of the following three things has to happen. You have to either move the wire, So here's a magnetic field. Here's a wire. Move the wire. Or, what do you think the second option is? Move the magnetic field. In a hydroelectric power station, water comes, you build this big lake from a river. Basically, you turn a river into a lake, creates this really, really high lake, and then this water goes through this penstock and through this turbine and generates electricity. What does this turbine consist of? Well, it consists of wire and magnets. And when the water flows past it, it moves one of them, either the wire or the magnet, and that generates electric current. Doesn't really matter which one you're moving though, right? You ever find yourself sitting in a car in a parking lot? Maybe mom or dad is in a store that you didn't want to go into. You're kind of nodding off for a second, and you're kind of, your head's kind of bobbing, waking up. All of a sudden you panic because this car beside you is backing out of the stall beside you, and you think just for a second that your car is rolling forward. You ever notice that? Some of you have. Apparently not as many as I thought. You know what I mean though, right? Like, it's indistinguishable, right? Like, for that brief moment, you think you're going forward and you panic just for a second, right? It is really weird. It doesn't make any difference which car is moving, whether it's the car beside you moving backwards or you moving forward. The effect on you is the same. It looks exactly the same. If we have a conductor moving to the right, or we have a magnet moving to the left, it doesn't make any difference. It's the exact same effect. Yep. I don't think so. No, I don't think so. No. Almost. Yeah, it kind of sounds a bit like it, but I don't think it's connected there. There is a third way, which is to change the strength of the magnetic field. If you strengthen or weaken the magnetic field, that'll generate a current as well. Remember, got a wire, got a magnetic field. Move the wire, move the magnetic field, change the strength of the magnetic field. Any of those three ways are going to get you an electric current generated in the wire. Okay. This diagram, the last thing I want to show you here today is just a justification as to how this happens. We've got a diagram here with two magnets, each with a north pole and a south pole. The magnetic field in between those two magnets goes this way, away from the north and toward the south. There's our magnetic field. Now we've got electrons in this wire. We've got lots of electrons in this wire, but let's pick out one electron. That one electron is going to go up. Why? Because I pushed it up. I didn't push that individual electron up, but I pushed the wire up. Maybe I've burned coal, which generates heat, which boils water, which generates steam, which rises and pushes the wire upward. Whatever. Like, something I did pushes the wire upwards, and along with it, the electron. So the particle has a velocity upwards. Whether it's because of steam rising or whether it's because I physically pushed it upward, whatever. The wire's moving upward, as are the electrons inside the wire moving upward. Now, regardless of what the cause is, I got a charged particle moving in a magnetic field. A magnetic field that's to the left, a charged particle that's moving upward. Now, let's do the hand rule for deflection for this. I got my thumb pointing upwards, because that's the way the particle is moving. That's the way the wire is moving. So the particles within the wire are moving upwards as well. My fingers point in the direction of the field, which is from north to south. My palm points this way, which means that there's a magnetic force on this electron this way. Well, if this electron experiences a magnetic force into the page, or into the board there, the electron moves that way, right? Isn't that what an electric current is? Moving electrons? We just moved the electron through the wire into the page, which means that there's a current that's going, an electric current that's going into the page. What have I just done? I pushed a wire and generated electricity. That's what I just did. That doesn't happen if there's no magnetic field, right? Got a wire, got a magnetic field. I moved the wire, I generated a current going into the page, right?